Section 36.4.5 Homogeneous and Heterogeneous Catalysis. A homogeneous catalyst exists in the same phase as all other reaction species. So the entire reaction system exists in only one phase, usually the gas phase or the liquid phase. It can be a solution. It can be a mixture of gases. A heterogeneous catalyst exists in a different phase from some other reaction species. Let me give you an example of homogeneous catalysts. Chlorine atoms can catalyze the conversion from ozone to molecular oxygen this way. And you can see chlorine may react with ozone to form O2 and ClO. So chlorine and ClO are both radicals. And ClO may further react with oxygen atom to produce Cl and O2. The net reaction is this: O3 plus oxygen atom to produce two molecular oxygen molecules. It can be catalyzed by the chlorine atoms. In short, a chlorine atom may lower this reaction energy barrier. In these reactions, all species and the catalyst are in the gas phase. Now let's look at examples of heterogeneous catalysis. So in this reaction, we're looking at a metal oxide supported platinum nanoclusters. So we have 1, 2, 3, 4, 6 platinum atomic clusters supported on a solid magnesium oxide surface. The reactant and the two products are in the gas phase. So we are actually looking at three different phases: the gas phase, and I would consider the platinum nanocluster as in one phase, magnesium oxide surface as in a different solid phase. So this is heterogeneous catalysis. One more example, we can use iron to catalyze the production of ammonia from nitrogen and hydrogen. The gas molecules of nitrogen and hydrogen will have to be first absorbed on the iron surface without bond breaking, without any formation. So you will have molecular nitrogen and molecular hydrogen absorbed on the iron surface. And then the iron atoms on the iron surface will start to gradually break the nitrogen-nitrogen bond. Well, you have a triple bond between two nitrogen atoms, one sigma bond, two pi bonds. So usually we're going to break one of the two pi bonds first, right? And then gradually form nitrogen-hydrogen bonds. So let's look at surface chemistry in a little bit more detail, because surface adsorption is very important. We'll look at its mechanism. So first, we'll define a variable theta. Theta is the so-called fractional courage. Let's imagine all these holes on the plate are surface sites or catalytic sites if we're talking about a catalyst. And then the blue spheres are the reactants about to be absorbed by the surface, all right? And then you can just count the number of sites in this picture. So we have 8 times 8, we have 64 sites, catalytic sites or reaction sites on the surface. And then how many of those sites are occupied? 1, 2, 3, 4, 5, 6. 6 are occupied. So in this case, this theta, the fractional courage, is defined to be the number of adsorption sites occupied, 6 of them, 6 are occupied, divided by the total number of adsorption sites. So in this case, in this picture, it's going to be 6 divided by 64. So it's less than 10%. So 9 point something percent, maybe 9.7%, roughly. All right. So if we have those gas molecules being absorbed on the surface, they can also leave the surface. And so we have 2 reversible steps, adsorption versus desorption. All right. So we can write out this 2 steps over here. This is reactant in the gas phase, reacting with the adsorption sites on the surface to form a Rm complex on the surface. So really, if you look at this blue sphere, this one is actually Rm on the surface. This is Rm on the surface. So this is R, this one is R, this is R, this is M, this one is Rm. Alright? And then this Rm surface may also undergo desorption to form this R in the gas phase and then unoccupied site. So now we can write out the equation for this theta. The fractional courage. Again, this theta can be between 0 and 1, or between 0% to 100%. Again, in this picture, I think it's roughly 9.7%. All right, so we can write out the equation for theta. It's a differential equation, d theta over dt. So this is the change of the fractional courage. Well, in this case, we understand that this step will increase theta. This step will decrease theta. So we're going to have 2 terms, one positive from the first step, one negative from the second step. If we look at the first step, we define this reaction rate constant for the adsorption process. All right. So what's the reaction rate? Well, supposedly it's going to be Ka times R times M, right? So first, Ka times R. Usually we use concentration in this kind of formula, but sometimes when we are looking at gases, it's more convenient to use P instead of concentration. After all, P is proportional to the concentration because PV equals nRT, so P is nRT over V, and N over V is the concentration. So P is simply CRT. So for convenience, we are using P here. What about this M? M over here. For most chemical reactions, we use concentrations, but now M are the surface sites. So really, we'll have to just use the available surface sites, which is the total number of surface sites, N, times the percentage of the unoccupied site, which is 1 minus theta. So that's why we get this as the production rate of theta. Again, N is the number of all surface sites. In this case, it's 8 times 8. That's 64. 1 minus theta is the percentage of the unoccupied site. Now let's look at the desorption. We need a KD here, and then we need to look at this occupied RM on surface. That's just n times theta. All right. So now we have this equation, the differential equation for the fractional courage, or the percentage of the occupied side on the surface. How do we solve this differential equation? We can solve this differential equation by, again, separating the variables. I mean, you can move all this expression to the left-hand side. You move dt to the right-hand side. So it's possible to solve this differential equation and see how theta depends on time, how theta changes with time. But for simplicity, let's just look at theta at equilibrium. At equilibrium, d theta over dt is 0. That's the definition of equilibrium. And this equilibrium is a dynamic equilibrium. That means just the adsorption rate is equal to the desorption rate. So we have this is equal to 0, and then you just simply move things around. You can get the expression for theta. Maybe I should just add at least, a couple equations to remind you that there are several steps to solve this simple algebraic equation. All right, so I added 2 steps here, and you can see we have these 2 terms that include theta. So theta is simply k times p times n divided by k times p times n plus kd times n. So over here. All right. N and n cancel. All right, so maybe I should just cancel n here just for simplicity. N is the total number of surface sides. And now we get the expression for theta. Theta is simply kp over kp plus 1. What is this k? K is the equilibrium constant for this adsorption, desorption process. So k is equal to this adsorption rate constant divided by the desorption rate constant. And again, for most chemical reactions, I think it's the convention to define the k to be the forward reaction rate constant divided by the reverse reaction rate constant. So adsorption in here is forward, desorption is reverse. Now we have this equation again, and suppose we have some data points. Let's say we measured this fractional courage, theta, under different pressure of the reactant. So we know theta, we know P. How do we calculate K, the equilibrium constant? Well, if we have only one data point, we plug them in, right? Just plug in the value of theta, plug in the value of P. We get the value of K easily. What if we have 100 data points? Well, you can use the same equation to get 100 different values of K and then take the average. But that's not the best way to do this kind of data analysis. It's better to somehow convert this equation to a linear equation and then do linear regression for this 100 data points. How do we do that? Again, we take the reciprocal of theta and we get this equation. So you can see 1 over theta is linear with 1 over p. If we plot 1 over theta versus 1 over p, we get a slope. The slope is 1 over k. The intercept is going to be 1, exactly 1. So after you make the plot, if your intercept is far from 1, there's something wrong with your experiment. All right. Let's look at a more complex situation. In this case, let's say we have a diatomic molecule in the gas phase. After it's absorbed on the surface, it decomposes into two atoms, and both of the atoms are bonded to the surface. Then how do we tackle this kind of chemical mechanism? Well, the reactions are here. Again, both are elementary reactions. It's just you have now R2 as the diatomic molecule. After R2 is absorbed, it becomes 2 of this Rm occupied sites. And these 2 occupied Rm sites can become this R2 in the gas phase again, and generate 2 unoccupied surface sites. So again, we're going to just write out the differential equation. d theta of dt is how fast this theta is produced. Again, theta is the percentage of the occupied site, or fractional courage. So this is how fast the percentage of the occupied site increases. So in the second step, theta decreases, the occupied sites decreases. So again, we have 2 terms. But now the first term, Ka times R2. So this Ka times the pressure of this R2 over here. And then times this squared, because you have a coefficient in front of the unoccupied sites. So n times 1 minus theta is the number of unoccupied sites. Now we need to square it. Alright, we need to square it. In the second elementary reaction, same thing. We have the rate constant K sub d times this occupied sites squared. So Kd times m theta squared. At equilibrium, we assume this theta over dt is 0, so this is 0, and then we get this expression. Okay, I'm not going to prove this again. I mean, it's just a simple algebraic equation. Or basically, just move this to the right-hand side, and then you take the square root of both sides, and then do a couple more steps. You will get the equilibrium fractional courage in this kind of format. What if you have experimental data and you need to analyze them? Well, again, you take the reciprocal of both sides. And this time, you need to make a Excel plot of 1 over theta versus 1 over the square root of p.